Okay, good morning everyone. For you who is in Bandung or in Indonesia, and hello everyone. It is very exciting that you're come from all over the world. So how are you? I hope you're well, staying safe and healthy. So first of all, let me introduce myself. My name is Lucky Puspitarini from Institut Teknologi Bandung, and you can call me Lucky. So I'm very excited here today to have opportunity to introduce you to our guest speaker, Dr. Muhammad Ikbal Arifyanto, who will explain to us about Milky Way and local group. So Dr. Ikbal is researcher and lecturer at Institut Teknologi Bandung. He was graduated from Institut Teknologi Bandung and Heidelberg University. His main research topic is about galactic structure. So before starting, let me inform you again about participant etiquette. So I will remind you again. So please rename your name as instructed. And then please mute your microphone and turn off your video unless the moderator or I allows it. Please give your full attention to the lecture. Type your question in chat or you can raise your hand. We will have the question session in the end of this session. Uh, and please do not annotate the presentation. Okay, without further ado, please join me in welcoming Dr. Ikbal. Dr. Ikbal, can you join me?
Yes, yeah. Thank you, Mrs. Lucky. Yeah, I'm very happy to be here in this summer school, and yeah, today I will talk about the first step in our understanding about the dark matter is to understand our galaxy first. So let me share screen. Okay. Uh, Wait.
Yes, now
No,
we
it's
can.
okay.
Yeah, it's okay.
Yeah. Okay. Okay, thank you. Now today, this is the first lecture for the series of Summer School on Galaxy and Cosmology. I will talk about the Milky Way galaxy. It is now about stellar and interstellar medium components. I'll separate these two lectures. The first one is the you can say the baryon component, and the other is the dark matter. Not really dark matter, but how we trace the dark matter in the galaxy from the local uh, density in the solar neighborhood and from the halo formation, and from the streams from satellite galaxy, and all near local groups from. Okay, let me start this outline. First, why we study the Milky Way. Second, about distant measurement and the era of Gaia. Uh, Third one about stellar components, about this, about the bulge halo, and also and about the galactic centers. And then about interstellar medium, and the last one's about the galactic rotation, because galactic rotation is our tools to understand the global distribution of dark matter in the galactic halo. Okay, first the nomenclature. Our galaxy come from Greek words galaxias. This is or galaxias Kuklos. It's a Milky Way or Via Lactea in the Latin words. Or in Indonesia, we call it Bima Sakti. It's from the mythology in the Mahabharata books. It's about one of the Pandawa, Bima. This is we call it the Bima Sakti. It's like still some people, I really don't know why our Milky Way, the patch of stars and dust in the sky called Bima. Maybe some of it's like dark, this is from Dewa Ruchi, when the Bima fight with great serpents in the oceans to find some holy water, something like that. This is what we call in Indonesia Bima Sakti, our galaxy or Milky Way. Rules to usually in the galactic astronomy we use the capital G or M for Milky Way for our galaxy, the galaxy or galactic with uh, capital G, and for other galaxy or extra galaxy we call a galaxy of galaxies with small letter. Okay. Uh, this is what we see the galaxy here in from the Gaia. What we see in the night sky, or it is from our data from about 1 billion stars in galaxy. So we see many stars in form a disk of galaxy, and then there's a bulge and a galactic center here, and we see here many black patch of dust, interstellar dust, and it is very important for star forming regions. And there's also the problems for us as astronomers to see many direction in the galactic disk, because this dust will obscure our observation and we cannot see the other side of the galaxy. Okay. Next, why study the Milky Way? First, because it's easy to study. It's a big, it's a near, it's a bright and close, and because we are in it, and allows detailed studies of stellar kinematics, stellar structure and evolution. We know luminosity on the spectral class of many stars. We can study the star formations, also the exoplanets, and to find any other planets in like our solar system, and also about interstellar medium. And online, we can also hopefully to detect the direct detection of the dark matter. Okay, can you see all this slide, right? Yeah, yeah. Okay. Yes. I'm sorry for technical problems. Yeah. Now we know that because we study the Milky Way, because of we can detail study of the star kinematics, structure and evolution, star formation, exoplanet, interstellar medium, and also we want to study about the dark matter. But the problem is, first we are in it. We cannot go outside our galaxy. Just like if you want to know the Earth is a sphere, so you can moving, sailing, or take a plane to circling the Earth. But the problem in our Milky Way, so because we are in, so there's a problem to see the direction. We cannot see all the directions in the galaxy. And then the distance are hard to determine. Some of near stars we can measure, so we want to try any tools to determine distance to other astronomical objects like stars, a galaxy, or some planetary nebula or some extra galaxies. This is our challenging as an astronomer to measure the distance as uh, accurate as possible. And also there's a dust problem. Dust is a serious issue because of dust we cannot see in some direction in the galactic disk. So to study, usually to study extra galaxy, so astronomers usually see in the above the galactic planes. To measure the distance, we have this diagrams to measure in the solar system scale. We can use the radar ranging measurement, like to Venus, to Moon, and use our knowledge about Kepler laws. We can determine the other distance uh, to all planets in the solar systems. But for nearby star, we can use the parallax trigonometric uh, method here. Uh, Before is because of the very small in order of arc seconds. It's very small angle, so we cannot see parallax in more in details with the ground-based telescope. So we need to use the satellite to diminish the effect of seeing and the atmosphere the Earth, because it is now we have Hipparcos in the 90s, and also we have the Gaia satellite to measure the trigonometric parallax for stars in the Milky Way. So for longer scale, so we can use the main sequence fittings in the Milky Way, or the Cepheid period luminosity scale for the nearby galaxy, and for a bigger scale, so we can use the type 1a supernova or Tally-Fisher relations and other standard candles to determine distance uh, to study our universe. So first, the parallax is part of the astrometry. This is the art of measuring stellar positions. This is so we astronomers cannot touch its objects or stars. We cannot start, or how to measure the like the temperature of the sun. So we cannot bring the thermometer to the sun or and go back there to know, oh, it's the temperature. So we cannot start touch the object. We cannot make the experiments, but we what we do is we analyze the stellar lights. For astrometry, it's directions, positions, changing in the positions or directions. For photometry, it's measuring the quantity, number of photon detected in certain time scale. Spectroscopy, we find the color and more about the energy, density, and also for polarimetry about polarizations. And the others is we use like a cosmic particle. We determine the not as a light but as a particle, the photons particle, and also we also determine the gravitational waves with different tools. This is our this picture sculpture in Australia from Tim Wetherer. Is representing the parallax measure for astronomical bodies. Yeah, this is stellar parallax. We measure the Earth is rotating the sun. So in this direction, we can see the star compared to the background stars and change after 6 months, and we can see the stars in different positions. So this angle is 2 of parallax angles. It is parallax angles is half of this angles. So we can using we know this distance as 1 astronomical unit. It's a tangent distance, so we can measure the distance from the sun to the stars. So if the stars come farther distance, so this angle also becomes smaller. What we see here like this, if we make a photograph of stars with background star in one directions for about 1 year, so we can see they circling around because relatively because our Earth is circling the sun. So you can see that this star is nearer to us than stars in the background. So this is parallel angle is larger than other parallax angles. So we can also from the distance, we can also this to measure uh, radial velocity and the proper motions. This is important for the astronomy. We can also changing star positions like this. This combination from parallax and the proper motions of stars. So the stars moving like this, but because the proper motions, the parallax is circling, but because the proper motion, the star moving in the direction, so we see like this helix uh, plots. So the accuracy of astrometric observations were increasing. First, we measure Hipparchus about 150 DC, measure the position of star about 1,000 stars, and then in 1600, this Landgrave of Hessen measured also the 1,000 star, and Tycho Brahe also measured the accuracy is about 1,000 arc seconds. So the first person who measured the parallax was Bessel. He measured one star with the accuracy about 0.1 arc seconds. And Jenkin, now we measure more and more stars using a program of trigonometric parallax programs in certain observatory. Now, to make a larger measurement, we have the Tycho and Hipparchus satellites here. They measure about 120,000 stars, parallax and proper motion. Now we have Gaia in 2015 was launched. And now in 2018, we have the catalogs about 1 billion stars with measure parallax and proper motions. This is the Gaia satellites from ESA, European Space Agency. And we have also to study our galaxy, we need not only Gaia, but also the ground base, because Gaia measure the astrometric satellites. It measures also the radial velocity, but only now we have only about 7 million stars. But to understand more about the stars, and also now we study the galactic astronomy, so we need a ground-based spectrograph, just like a survey like Apogee, Lamos, Gala, and Brave, to study more, not only the radial velocity, but also the stellar chemistry. Here, what we know about our galaxy is artistic view. You can say it's our galaxy, Milky Way. Here it's a position of our sun. Our sun's here. And in the Hipparchus survey, they cover only about 100,000 star, about maximum is about a few hundred parsecs. Here we maybe until maximum is about 1,000 parsecs star distance. And but now in Gaia we can measure bigger part of our galaxy. We study more detail with good distance measurement from the parallax trigonometry. As this is Gaia, this is not a map, but this is real stars measure about 1 billion stars measured using Gaia satellites. So we can determine the positions, color, distance, and also its proper motion. So they moving here. Why it's important? Because we also can determine the velocity of star. If we know the velocity, we can using our knowledge about the potential of our galaxy, we can measure the dynamic of our galaxy. So dynamics, we can measure the total mass of our galaxy, and we can compare with the baryonic mass, the stars and the gas, and compare if there's any hidden mass like a dark matter. So we need to understand uh, the dynamics of the Milky Way. Here, data from the Gaia data release the second data Gaia release. The Gaia measure about 1.6 billion stars with position and brightness, and 1.3 star with colors, red color and blue colors, and about 1.3 billion star with parallax and proper motions. Uh, there's only about 160 million star with surface temperature, 7 million star with radial velocity, and also other about 80,000 star with radius and luminosity. Not so many, but it's very large data. So now we have a big data in many cases, so we can also use our knowledge about big data to study our galaxy from this Gaia data release. This is the first Gaia data release from 14 months of data, and now we have Gaia data release second. We have 22 months of data. This is flux and colors, and this is the amount of dust and gas in from Gaia measurement. This is radial velocity data from about 7 million data. So you can see this is the blue. It's blue shift and this red shift. So you can see in the edge on side that our galaxy it really rotates. This is there it is redshift and blueshift like circling, and you see there's a different direction in near the center of the galaxy. So from Gaia science we can determine uh, position some uh, uh, like solar system object. We can measure the stars nearby the suns and also the galaxy, the Milky Way and the halo and the globular clusters nearby the galaxy, and also we can also study the celestial reference frame using distant quasars. Now we start with the Milky Way as we know it until now. This is our galaxy schematic view. This is a galactic nuclei. This is a bulge galaxy, and there's also a galactic bar. We have a spiral arm here in this direction of our gas moving. This is a rotations of our galaxy. And in the disk, we have a thin disk and thick disk star, and also this part near the sun. So we have many structures in the galactic disk, and we see also our disk is not flat, but kind of warping. It is down and it's up. We can see also the molecular clouds and also the globular clusters in the center, in circling the center of the galaxy, in the galactic halo. Now, for star, we see open clusters, many as a part of a disk populations. This is a young population. We have many about now we study about 1,000, more than 1,000 open clusters in the galactic disk. This is from the Gaia data. We can measure from the proper motions or proper motion data. We can separate. This is a field star and this is the Pleiades star. So we can select the Pleiades stars then from the background star, because in the open cluster the problem is we see many stars in the galactic disk, and there are some cluster stars, open cluster here. The problem is how to we select this cluster star from the foreground and from the background stars. So one tools is to study the proper motions of open cluster. This is very different. This is Pleiades, and we have many from data of proper motion. We can select uh, uh, many open cluster using this method. This is the parallax, trigonometric parallax from Pleiades, so we can measure the distance very accurately. And this is from the uh, magnitude in G band and the blue part and red part. You can plot the HR diagrams of open cluster is was selected using age of the open clusters. This blue one is a young one, about log 8. It's about 100 million years. This is a young one, and become yellow, greens, and red one is the old open cluster with about uh, 1 billion to 10 billion years, or in less than 10 billion years. This is distributions of our open clusters using from the Cantor Gaudians et al. In 2018. This we can measure also the local spiral arm. This is Sagittarius arm, local arm, and Perseus arm. And in the left picture is new open cluster found using the Gaia data. This is a globular cluster. The old populations from our galaxy is, you see, it's different. It's more clump and more dense star and more stars in them. So this using the proper motion, we can also select this. This is the 47 Tucana, and this is from the stellar halo. We can also use this as a stellar halo to measure the part. This is many about 100 globular clusters in the Milky Way. This is the HR diagram from our globular clusters, and this is the old population. This is horizontal branch, and its age is in separate with the metallicity. This is a more metal poor, and this is a more metal rich. Metal poor, you have like a UV excess. It's more bluer than the higher metals. Now we study the star populations in the Milky Way. This is a schematic view from H-on. This is our bulge galaxy, and the disk. There's an extreme disk from dust cloud, and also the blue one is a thin disk. The green one is a thick disk, and also the galactic halo. This is this scale height of thin disk. It's about 300 parsec. Thick is about 1,000 parsec, and then there's a halo with a more spheroid system. From the bulbs, we can measure distribution. It's like a spheroid, spherical, with density depends on R power to minus 2.2, and the population of metal-rich and super metal-rich stars here. And there's a relation between rotation velocity and the metallicity is in here. And we have a thin disk population 1. This is a young population 1. The density falls with the exponential disk with the scale heights about 325 parsecs, and it rotates with the same as the sun rotates the galaxy. About the velocity is about 220 kilometers per second. And also the thick disk one, older disk. This is with the scale height about 1,000 parsec, but rotation is more or less about 180 kilometers per second. But the distribution is more higher than the thin disk. So, and then a halo, it's a spheroid distribution. The density relates to R power minus 3, and it's metal poor. And rotation is about minus 40, just like a counter rotating with compared to the disk here. And to study a star, we need information, our knowledge about the stellar density, stellar luminosity functions, and stellar initial mass functions. From stellar density, we need as a star count, a star counting in the direction, and how many stars with a certain magnitude, and measure in the area. Uh, this is stellar density, number of star per unit volume uh, in the direction L and D. This galactic coordinates. The complication is we have extinctions, and we have missing faint star. Uh, because of limit of detection of telescopes. And from here, we can measure the density locally near by the stars. This is the distribution of A stars, F stars, and A stars. So, as you see, more earlier spectral type have a shorter scale heights here, and older stars, uh, late type spectral have a larger scale heights. From density, we can measure the local luminosity functions. If we know the distance, we know the spectral type, so we can measure the absolute magnitude. So we have a star luminosity function. This is a distribution of star per certain uh, bins of absolute magnitude. From this, we can see how bright stars are more or less in numbers than the faint stars. This is from the nearby luminosity function from the Hipparcos data. Yeah, always more faint stars, low mass stars than the bright stars. And from the star luminosity function, we can, if we know the relation of mass luminosity relations, we can measure the initial mass function from present day mass function, and we measure about if we know the age metallic relation and also age mass relation, we can measure the initial mass function, distribution of mass in newly formed populations before it evolves. Yes, so from this we see that high mass star is less in number than the low mass stars. This is many uh, measurement of the initial mass functions. First derived by Salpeter in 1955. If we have a Salpeter slope is about 1.55 minus 1. So higher mass become less in numbers. And from our knowledge of luminous functions and density, we can measure the what's it, from the star fundamental equation of stellar statistics. This is distributions of star in different directions. So we can map uh, star distribution in the galaxy. Also, starting from the local, because the distance is very accurate, so we can, and then with the Gaia data, we can work until 1 kiloparsecs, the complete samples. Yeah, from this distributions, we can measure in the z directions and to the in the galactic uh, perpendicular to the galactic plane. We can measure the number density of star poles. This is from the SDSS data. This is sample from the SDSS to the North Galactic Pole and the South Galactic Pole. This is our sun here. The red is with high density, and you can see this. This is a subset of our galactic disk. You can see this disk become thin here, and we can measure the density with the z direction to up and down. Our density into the galactic uh, uh, graphic plane is fall with the exponential. With h is a scale height. It's about 300 or 350 parsecs. This is from with different colors from the SDSS data from measurement of Uric in et al. At 2008. uh, in the distance from 8 kiloparsec. There's a this is a vertical dash line. This is the position of the sun, because our sun is not in the galactic, in the zero z equal to zero galactic plane, but about 10 or a few parsecs below or upper. Sometimes there is some upper in the galactic plane or below it, different measurements. And this scale height is not fixed. It relates with main sequence. Younger one have a smaller scale heights, but the older main sequence have a larger of scale height. This is indicative of formation and dynamics. Stars form in the close of the midplane near the interstellar medium. So the younger stars, like the OB stars, they have very close to the disk, and so also the scale height is about less than 100 parsecs. But as a star older, they moving with the dynamic interaction, so they have many random velocity increase and the disk thickens, so the density become uh, higher. And also we have also the thick disk, the thicker part of our disk here, and uh, it's a scale height about 1,000 parsecs. First found by Gilmore and Wright in 1983. They call it a thick disk. It's a different part of the disk. So the disk only, we have two disks. This is a thin disk part, and this is a thick disk part. So different scale height. This they are. This is new data from Judy et al. In 2008. This is a thin disk, and here part of thick disk. It's older stars in the thick disk, and also the more metal poor compared to the thin disk. Here, the scale height is around 600 to 900, sometimes to until 1,000 parsecs. The scale length is density from the galactic center to the outer galaxy. In the galactic disk is about 4 kiloparsecs, and only small number. This is number density normalizations. It's for every 100 stars around the suns. Only 4 until 11 belong to the thick disk, and maybe only one, less than one, belong to the galactic halo. So, but if our sample become larger until 1 or 2 kiloparsec, we can detect many thick disk or halo stars. And we have also the thick disk have a larger velocity dispersion, or we call it the hotter of thin disk, hotter than thin disk. And the stars are older and lower metallicity and alpha abundance. This is from metallicity. See, we can measure this is if iron to hydrogen, Fa over H. This is Fe, and this is alpha elements to Fe. So we can see there's thin disk stars with the high metallicity here, and then we can separate the thick disk components from here with larger alpha elements, and this part is the halo part of the halo population. Alpha elements is part of the triple alpha from the process, like oxygen, neon, magnesium, and others particle higher than hydrogen and helium. This. And spectroscopy is very tough to do because we need a high resolution spectrograph and a good big telescope to detect many stars with elements of the stars. And we have a galactic bulge here. This is like the center of our galaxy. This is scale height of thin disk near the sun is 350 increased with the galaxy, and this is near the bulge centers we see in the near infrared using near infrared data. This is from Kobe data. This bulge luminosity is not this like like a spheroid star. So you can fit surface density of our bulge galaxy, like just like in the elliptical galaxy or in bulge of spiral galaxy using the focal law. This and density, and we can measure our bulge is about uh, the scale radius scale is about 0.7 kiloparsecs. A new measurements using the infrared data, K-band data using red cloud, so we can measure the bulge. It's like the X shapes, uh, like this. It's the orbits of stars in the our bulge. Near the bars, also we have the galactic bar here, dynamically stable and found in many these galaxies. This is our suns, and we see that our bulge have about angle maybe 20 or 30 degrees here, and this is the density of uh, bar and bulge with different measurements here. There's a dust line in the prominent in our bar cousin, and evidence of the orbit of gas in radio observations and non-circular motion. From the 21 centimeter observation, we have about 3 kiloparsec expanding arm, like a bar moving toward us in circling with 50 kilometer per second. So the radius is about 4.4 kiloparsecs, and angles is about 44 uh, degrees with respect to line of sight to the galactic centers. Sorry, not the 20 or 30, but about 44 degrees. It's thicker in the plane of the galaxy in the Z directions. So we have now into the center is hidden behind the gas and dust and invisible in optical light. Optical light we cannot detect because of the dust preferring us from to see the into the galactic center. So, but we can see it in the infrared. It contains a denser star clusters, with stellar density strongly peaks near the center, and also radio high, and also an extra in the source Sagittarius A stars. So this is a recent measurement from the Guest et al. Team from Guest. They measure the few stars. They call it S stars near the galactic center using the infrared data, and derive the supermassive black hole mass with about 4.1 million solar mass in the center. So we measure this like you see this circling globe, so we can using we call it the proper motions, and we measure if one using the Kepler laws, we can, so this is the distance about 8.3 or 8 kiloparsec to the galactic centers. We can measure the period in one circular one orbit near the circling the galactic center. We can measure the mass of supermassive black hole. That's like this is from almost one orbit, so we can measure this. Yeah, and other features in our galaxy is the galactic warp. Here we have a scale height of neutral gas is about 160 parsec in here, and increase dramatic here. This is the median Z. This is X and Y. This is galactic center. This is the sun here. So the distributions in the median, this is the blue one is below the galactic disk, and the red one is upper the galactic disk. So you see in these directions, most of the stars are below the galactic this, and this is in the direction is most of the star in the upper of galactic disk. Though our galaxy is not a flat one, but we have a warp with angle about 50, 15 degrees relative to the galactic planes. Using the hydrogen measure is about from is about 13 kiloparsec from the galactic centers. This is a schematic view of the galactic warp, and this is our measurements using Cepheid variables the warp, and this is from the OB and red giant brand stars. So you can detect this. OB is blue one, and the red giant brand is red one. So you can detect this galactic warp. Uh, okay. Okay. Last one is about interstellar medium before rotation galaxy. Our galaxy is not only a star, but there's also gas and dust between the stars. Stars from the form from the interstellar medium, and then stars will return the material into the interstellar medium. It's about 10% of all baryon reside in the interstellar medium. Composition is about 90% hydrogens, 50% in form of atomic hydrogen, and 50% in the molecular, and 9% in helium, and 1% in other elements, everything, all heavier than helium. Heavy elements are usually formed in the dust. Then so we have dust as bigger molecule, complex molecules. About 0.7% in the ISM is in form of dust by mass. So we can detect the interstellar medium from the long wavelength using the radio continuum. We have also the hydrogen, atomic hydrogen from 21 centimeter measurement. This is a short wave radio continuum, molecular hydrogens, and also cool dust from in the far infrared data. From the shorter wavelength, we have a warm dust, dust that emits the infrared radiations, and also from the cold stars here in the infrared, and also a normal star we have to see in the optics and many dust layer. And you can see here in the near infrared data, you cannot see this the dust. We can see many stars in the bulbs and in the galactic disk, because the dust cannot the infrared radiation can penetrate the dust. And also we have the X-ray and also the gamma ray with different sources. So what different types of nebula? We have dark clouds, we have reflection nebula, we have a planetary nebula. The first one, if we have a dark cloud, this is a part of dust. This is covering many stars. It's like a hole. This is not a black hole. It's only a dust covering the background stars from the light from reaching to Earth. This is. But if we see in the infrared image, we can see the stars in the background. The stars here maybe are the foreground stars, but here we can detect this using infrared region. And usually the dust and the molecule are related. This is a region of the dust, and also then from the molecule of hydrogen. It's related with the dust. And also there's extinction radiant in Orion Nebula, where and this is the optical infrared, where star forming region here. This is the warm dust in the Orion regions. This is a Orion belt, and this is the Orion Nebula here. You can see this galactic hydrogen molecule, and also it is another reflection nebula, like a nebula as a dust as a scattering. Usually it's near hot stars, and there's a dust around them. The dust become scattered the blue accidentally into to the sun, so we can see the blue part of the light scattered into our directions, and the other to different directions. It's because there's a source of hot stars here. Uh, like say the other examples is like in Pleiades, not hot star, but there's some huge uh, interstellar dust here, so can scatter into the blue star. Now, usually in the reflection nebula, there's some hot stars, uh, uh, ionization nebula here, and there's also some of the blue part is the part of the reflection nebula. In the H2 region, this is the ionized nebula. Uh, this is a new star formed here. It's like an Orion Nebula. This is like O type stars. So the stars emits mainly in the UV light. So the energy can uh, ionize the electron from the ground state to infinity. So they absorb the UV light from the star, the OB stars, and then the electron were free from the proton. So we can we call it ionized nebula H2 regions. This make usually if the stars were hot, they around the stars ionize the all the hydrogens here, so make like a sphere. We call it a Strontian spheres, photoionized by the UV photon in from the stars. And the outside there's a recombinations region where uh, the electrons more attracted back to the second set or the ground state to the proton, to the hydrogen, forming the hydrogen neutral again. This is in interstellar near star forming region. This is stars not only form one by one stars, but in one molecular cloud they uh, they form one cluster of stars. So most of stars in our galaxy form in a clusters, in a like open clusters, like this. So here, like cluster forming regions, usually in the natural hydrogen, and this is part of the ionized hydrogen. As long as and when the clusters become older, so the gas will dissipates uh, outside cluster. So the stars uh, evolve, and the cluster also evolve dynamically, and then they separate all the stars, eject all the stars. Firstly, the low mass stars become ejected from the cluster centers. Then here we also here in ITB we make a simulations on binary star cluster formations using like that the clusters stars form star cluster is not like spherically, but in a fractal way, not in the part from the merger from the small clump of stars clump, and then make a higher order. So this is uh, from about simulation from the very clump stars and evolve into one clusters or into separate uh, cluster. The cluster will evolve uh, from the gas, and it can be cluster will die if they dissipate all stars into the for galactic disk stars. But if it survive for the long times, and so the cluster is still clump with tiny. It depends on the initial mass of the clusters. Also here, they're also hot in interstellar medium. in supernova, like in Cassiopeia, not only gas in cool gas like hydrogen, but there's also gas, hot gas from the supernova explosions. It's very hot and emits in the usually in X-ray, and we can see the X-ray region. Then also it's alpha from the shocks of the supernova. Near the cluster we have near the sun we have the what we call it local bubble. It's like a hot region near the sun, and the sun is inside this bubble. It with low density uh, hot thin gas about 0.001 atom per centimeter cubic. This we our sun here, and it's Sirius, and the other it's the yellow part is uh, like a gas, flatty gas to form stars here. And this map of the local bubble, not really spherical, but because of many complex region in the interstellar medium, so bubbles is some kind like this. There's also Pleiades bubble and other bubbles. This is a new local bubble from uh, map from the dust and also from the X-ray map. This is our atomic hydrogen clouds. This is star gas star cycle. So star was formed from the gas into atomic hydrogen clouds, from the molecular clouds, and from star formations, and then nuclear fusion in center of the star starting, and then evolve depending on mass. Low mass become a planetary nebula, the high mass become a supernova or any stellar winds, and returning the gas back to the interstellar medium. This is the cycle. Here's our spiral arm mission from the interstellar medium, usually using gas clumps here. This is Sagittarius arm from and Centaurus arm from the our from the sun, optical feature from molecular clouds, from star cluster, younger star clusters. We can make some to find. The problem is we are in our galaxy. We cannot outside, so we can map the gas and the younger stars that form the spiral arm of galaxy. Okay, this is the I will continue to the last part. I hope it's okay. About 10 minutes. The star in galaxy is moving. This galaxy, most of the star in the galaxy is moving like a carousel, like this, circling the galactic center, and also go up and down like the yellow part. This is a D star orbits, the same orientation. This is like this, then little up and down. If you like a carousel, and if you stay in a horse, the horse will go up and down, and the horse circling the pole, and you measure. This is like these stars moving like that. But the older one, like a halo stars moving in the random directions other than this. Also the bulbs also moving in the random direction. So it makes the spherical halo and also bulbs. Near the suns, we can measure what we call its standard of rest. If the subsets of solar neighborhood about 100 or 200 parsecs, so you can measure all the stars moving in randomly, so we can make like a standard of rest, center of motions, so we can measure that the velocity of the sun according to this local standard of rest, and we can measure this velocity, circular velocity, and we can also measure the mass of our Milky Way from this. So the galactic rotations dominantly, and thus, so from here you should see if the solid body solid body if we have like this, it's a solid body. If it is centers and the circle we have two in the same time they arrive with different positions here. It is the same angular velocity, but the different rotation velocity because the longer distance from the center have a longer orbits, but they are arriving in the same time. So we can plot here distance from the center to rotation velocity. The further distance become higher in rotations. Our solar system form like a Keplerian orbits. Mercury, Venus, Earth have farthest is nearer to the suns have a highest velocity, and then all other planets come. It relates to r power to minus 1/2. This is the Keplerian. But the flat rotation curve, this is the rotation velocity is flat, but the angular velocity depends on 1/r. This is we measure also the shear and rotation of the velocity fields near the sun. We can measure in the direction of sun. This is our sun, and we measure. We assume it's a differential velocity. We assume first that our galaxy it's like Keplerian motions, and because this near to the galactic center become faster, and then further to from the galactic center become slower. And then we measure using proper motions and radial velocity. This is the plot from the radial velocity with respect to the galactic longitude, and this is the proper motions. From this we can this triangle, this galactic center, sun and stars. This is the velocity of rotation velocity, and this sun's rotation velocity. We can measure the star rotation velocity from the sunset. We can measure also this relate to the Ort's constants here, A and B. This is to measure Ort's constant is about A is about 14.4 kilometer per second per kiloparsecs, and B is measured minus 12 kilometer per second per kiloparsecs. How we measure the rotation curve? We can use also natural hydrogen from the 21 centimeter. This is spin flip from the hyperfine structure, hyperfine splitting. This antiparallel. This is a parallel is higher energy than the antiparallel. So if they back to the initial spin electron, so they emit a photon in wavelength about 121 centimeter. So we can measure the emission from the 21 centimeter. This is radial velocity or frequency, this intensity. And there is one, because we measure the rotations in this part, is we can measure the A, B, C, D. But this C, we compare that the velocity coincides with the rotation's velocity. So we can see that the C is the highest velocity and radial velocity. So it represents the rotational velocity of the object here. We can measure from this. We can measure the distance using tangent point method. So using tangent point method, also we can measure this part. Is like 4. It's 4 always like in the right part, in the left right part, and also if the other way around, so they have in the left part, we can measure only this one, this part. We can measure the distance using the tangent point method. So we can measure the this is a Milky Way rotational velocity from the longitude and latitude from the flux, and also this is the from radial velocity. So we can see it's actually it's two two sinusoidal plot. From that we can measure the distance and measure our rotational velocity. This is a we call it mass concentrate in the center. It's a part, and this is sun here. This is from data from star and also from the hydrogen molecule, hydrogen neutral, and this is from other method, usually using distance to the molecular cloud, if you know the distance, and also stellar emission line. If the galaxy follow the Kepler motions, it should be down like this. But uh, further from the galactic center, the rotation curve is still flat here. So here, this is a new from IRGAM. This is from the data, rotation curve data, and this is a fit model. The model comes from a contribution of the galactic bulge here near the center, the galactic disk, mainly in about here until 8 or 12 or 14 kiloparsecs from the centers. But the problem is the velocity is still flat. So people assume there's a dark halo. The halo population is still uh, no many stars we see in like globular cluster or RR Lyra or many hyper velocity stars. But the mass of this uh, further part of the galaxy we cannot see. This is what we call it is the dark matter, or we can the missing mass or dark matter like this. So if you plot from this part, and this is the spheroid part or the bulge part, the totals will be only like this. To become flat, we also add the corona or the dark matter halo like it to become the plot become still flat until 20 kiloparsecs. Yeah, what we talked about just now is about this component. Yeah, we do not talk yet about the halo distributions, about the dark matter dominates this area in our galaxy. This is only luminous matter, the star and gas. And we will, in the next session, we'll talk about the dark matter and also the halo, how complex is our, it's like near a galactic neighborhood. How complex is our local groups with the small satellites, small dwarf galaxy, and also other uh, Andromeda galaxy, and relates with this dark matter. Okay, thank you. I will give to Mrs. Puspitarini. Looking, please.
Thank you very much, Dr. Ikbal. It's very, very wonderful presentation, so many information. I will read you some of the questions from the participant. So the first question is from Fernanda Putra Pratama. So is there a method to observe the star behind our galaxy center? Yeah, please, Dr. Ikbal.
Yes, thank you. No other method. Usually, there's some region you call it a Bardis window in near the galactic center. It's like a hole. There's some. It's the only coincidence. There's no dust in the surface, so we can see. Go to the back of our near the galactic center, but to see the background, there's I think no other way to observe the other part of the galaxy.
Yes.
I
It's
think
very difficult. Yeah.
it's very difficult.
Okay, the second question is from Amir Shahreza Fadila. So the question is, why do the galaxy's halo is more spherical than the main part?
Yeah, it's very long. It's related to the what if you understand the public lectures before about our model of our universe. There's formations of the cold dark matter. Cold dark matters uh, forms from the small clump of what we call it subhalo and become bigger and bigger. So its the distribution is more spherical in the cold dark matter. Assumes that the distributions, the interaction of only gravity in the dark matter. So they make clumps and they what we say the gas hydrogen gas from the intergalactic medium. They uh, catch the gas and the gas collapse and make stars, and stars that make the galaxy, small galaxy, and then uh, merging process. This is I will explain later in the second session about this
Okay.
formation of galaxy. Yes.
Okay, so we can go to the next question
Yeah.
from Rafif Labani. So does the functional form of the IMF depend on the model of the dark matter used?
No, IMF is I think it's free from the
Initial mass
dark matter
function.
initial mass function. Yes, it's free from dark matter because we measure the usually from star in the solar neighborhood and uh, and actually and also from star cluster nearby, and most of this IMF it's quite similar in the slope if you detail in the if there's a one slope or two slope in the mass function. But I think it's yeah, in the small scale it's free from the dark matter uh, model. I think so.
Okay, so I will go to the next question from Raed Ziad Ahmad. When we want to estimate the mass of the galaxy, we already count the dark matter, not only baryonic matter. So is there a way to estimate the baryonic matter of the galaxy more precisely?
Yes. First, we measure but apart from our galaxy, we measure only the density of stars and gas, not really precise because uh, roughly because we measure the because we are inside our galaxy, we cannot see all the stars, so we can count all the mass, luminosity mass from stars and gas. So we use the model of like a disk, usually disk from star disk, from gas disk, and to estimate the mass from the potential of the stars. Actually, from the nearby stars, we can nearby region, we can measure all star inside like some maybe like 100 parsecs regions. So we can detect all stars inside, and we can measure this estimate the mass. But still, there are the problem of our telescope. More bigger telescope, we can detect more uh, less luminous stars and like M stars or LT dwarf stars. It's very faint, so it's the problem if we cannot see. And many faint stars, low mass stars, are many in our solar neighborhood. So there's still problem to determine more accurately. Okay.
Yeah. Okay, I will go to the next question from Arif Nur Rahman. Why do astronomers think that supermassive black hole lies at the center of the Milky Way galaxy? So why supermassive black hole
Sorry, why?
lies at uh, why so
I think that
why do astronomers think that a supermassive black hole lies at the
uh,
center of the Milky Way galaxy?
yeah, okay. Because we observe a star near the centers, and the stars like uh, circling one center, but we cannot see the center. In other way, using the radio and the X-ray, we can see there's a bright spot, very high energetic region in the center, in the Sagittarius A star, we call it there. And also we observe many star and star cluster circling these regions. So from the infrared data, we can determine the orbit of one or few stars near, and to make sure using Kepler laws, second law, so we can measure the distance though. But the problem is this mass of 4 million solar mass inside small regions in the near galaxy center. So our knowledge is, so it's a supermassive black hole from our current knowledge. So no other way. Maybe I don't know. I think the best. No, we know it's like a supermassive black hole set. So because we observe also in the other galaxy. Okay. Yes.
Okay, for the next question is from Muhammad Sofyan Shafi'i. What caused the shape of the Milky Way galaxy to look like a rattle in simulation?
What rattle in simulations?
Ya, rattle
Is it like,
berdetak.
yes. Oh, okay. It's because what is I don't understand. Rattle in simulations is what can you simulation?
Yeah. Okay, maybe we can postpone this question. We can go back again to confirm
You
to
can
Sofwan.
please write more, explain more. I will
About
answer
the
later.
question.
Okay. Yes.
Yeah. So we will go to the next question from Atma Tiwari from Nepal. Is the distribution of dust in the local bubble of sun is spherical in all spectrum like infrared and ultraviolet or X-ray? Why?
No. Mrs. Lucky should explain more clearly because you work there. Yeah, it's not as spherical because the interstellar medium is very complex regions. There are many pressures, different temperatures, and different densities. So and also in the galactic disk, the pressure of the like a density wave. So not so the bubble maybe originally it's like a spherical, maybe, but because of the complex move there, so they're pressed in the region of the galactic disk, and also there are some other mechanism also. But in the galactic above and below the galactic disk, there's lower density of gas. So the local bubbles can expand like make a sometimes like we call it a local chimney if the open supernova explosions. There's also we can outside the galactic disk like chimney. So it's not like more pressed, like it's not really spherical because very complex.
Yeah. It's asymmetrical bubble actually.
Asymmetrical bubble. Yes. Yeah.
Okay, I will go to the next question from Rafi Adnan from Bangladesh. Do the dark matters have any influence on the evolution and the current shape of our galaxy?
Yes, of course, of course. It dominates our evolution and shape of our galaxy. Uh, yeah, because our galaxy formed from the clump or substructure of the dark matters, and they accrete intergalactic gas and form stars, and all this becomes like a globular cluster or dwarf galaxy, and they merge together to become a larger galaxy. So it's very important dark matter to the evolution and current shape of our galaxy. Okay.
Yes. Okay, I will go to the next question from Arif Nurrahman again. So, is dark matter responsible for differences in observed and theoretical speed of star revolving around the center of the galaxy, or is it something else?
Yeah, dominates it's from dark matter. We only see the stars moving according to the potentials of the galaxy. So from the potential of the galaxy, we know distribution from stars, from the gas, from the stellar bulge, and stellar halo. So we add this, it's still not making a flat rotation curve. So you need additional dark halo, halo dark matter, yeah, halo dark matter to this. It's also, uh, yeah, but the observations, maybe the observation in the more distant than the galactic center. It's maybe it relates to the galactic halo. Yeah.
Okay. So the last question is from Suruchi Sahi from Nepal. How do we study the distribution of dark matter in particular galaxy?
Uh, in particular galaxy, first we measure the velocity. We cannot see the dark matter, but we can. But the dark matter interact with the in the gravity force. So we measure the stars, the gas moving with the gravity according to the potentials gravity uh, of the dark matter halo, so we can trace back its movement using our simulation, so we can know the form or the structure of the dark matters. So we from the data, velocity data, kinematics data, so we infer the dynamic simulation to know the dark matter. That's it.
Okay. I think there is. Oh, sorry. There is another
One
question.
more. Yeah.
One
Yeah.
more. Do dark matter have any influence on Jean's mass of the gas cloud, which will make star in the future? And can dark matter create the gravitational collapse for the gas cloud having mass less than Jean mass to form stars? Maybe.
Yeah, from star scaling from star forming regions, I think the dark matter its contribution is low, but from the star formation in the formation of the galaxy in the scale of the dark, it's very important for the first we call it first generation of stars. I think it's very important domain of dark halo, but for star forming region in nearby in the galaxy in the galactic disk, I think contribution of dark halo is uh, low. It's purely a baryonic process, I think. Yeah.
Okay.
Yes.
Okay, thank you very much, Dr. Ikbal Arifyanto, and thank you very much for all the participants. You've been very wonderful and respectful. So before we end the meeting, let's have a photo session together. And then after this, you can have a break, you can have rest and lunch, and then we will come back again to the next session. So please turn on your video, everyone.
Okay.
Okay. Dr. Anton will help me to take the picture.
Okay, maybe yeah. Need yeah. Okay, I'm waiting for participants open their videos. Let me check first. Okay. Okay, I will start now. Okay, for the first slide, I will take your picture now. Please be ready. Okay. Okay, 1, 2, 3. Okay, the second one. Let me check. Okay, second one. Okay, done. Thanks.
Okay. I will also ask you to turn on your microphone, and let's give a big applause to Dr. M. Ikbal Arifyanto.
Thank you so much.
Thank you very much.
Thank you very much.
Thank you, Professor.
Thank you very much, Pak Bang.
Thank
You're
you.
welcome.
Thank you very much, Mr.
Yeah.
Iqbal.
Okay,
Yeah,
so
you're welcome.
see you in the next
Thank you
session.
very much.
Thank you, Mr. Iqbal.
Yeah, welcome. You're welcome.